Hi everyone. In this video we're going to look at Chapter 18. And in Chapter 18 we're going to study paired data. We're going to conduct a paired t-test and a paired t-interval. So paired data, this chapter is going to combine what we learned with our 2-sample t-tests and t-intervals with our 1-sample t-test and t-interval. So I want to look at the difference between independent samples, which were a requirement for a 2-sample t-test. And I want to look at how that's different with paired data or paired samples. So we have an example here. It says a drug company has developed a new drug that is designed to reduce high blood pressure. The researchers wish to design a study to compare the effectiveness of the new drug to that of the old drug. So we have two scenarios here. In the first scenario, we could have 2 samples of individuals, so 2 different groups. One sample is given the old drug and the other sample is given the new drug. And then after several months, their blood pressures are measured. So these would be considered independent samples, and we would run a 2-sample t-test or t-interval. But another way that we could do this is with paired data. So we could take a single group of individuals. We could give them the old drug for a month and then measure their blood pressure. And then switch drugs and give that same group of people the new drug for a month and then measure their blood pressure again. This is an example of paired data, and we would conduct what is called a paired t-test or t-interval. There's a few kind of classic examples of paired data. This is one that we describe as a before and after. So you've got the same group of people, you collect data of what happens when before something happens, and then you take that same group and collect data after something happens. Another example would be, say you have the same group of students in 2 different classes. Say one's a math class and one's an English class, but it's the same students in each class. And you wanted to compare data from the math class with that of the English class. But because it's the same group in both classes, that would be paired data. Another example would be family members, say siblings. So you would have different subjects in each sample, but they have a relationship to each other. So maybe the first sample is data on the oldest sibling, and the second sample is data on the youngest sibling. And you want to look at the difference between those data. There's a natural pairing there. So I want to use an example to talk about how we set up this pairing and the notation and the relationship this has to our 2-sample t-test. So we have an example here. It says, suppose we select 16 volunteers and they are given a test in which they had to push a button in response to the appearance of an image on the screen. Their reaction times are measured. Then the subjects consume enough alcohol to raise their blood alcohol level to 0.05%. And then they took the reaction test again. So this is an example of paired samples because we have the same set of individuals in both samples. So we have the data before they consumed alcohol and then the data after they consumed alcohol. So I want you to look at this table and notice that they actually set up the table in the other direction than how they explain the problem in the example. So notice that the reaction times for after they consumed alcohol are first, and the reaction times for before they consumed alcohol are second. So this is just a preference. It's not a requirement. It's actually not something that I do, but I do want to talk about why you might see this when you're looking at a math problem in the textbook or MyLab. So when we look at groups of data and we're comparing the differences, we subtract. So when we subtract those sample means, they are assuming that the data from after they consume alcohol is going to have a slower reaction time, meaning that the amount of time is greater than before they consume the alcohol. And because they're subtracting, if you take a greater value minus a smaller value, you're going to get positive numbers. And some people just prefer to work with positive numbers, so they set up their information ahead of time with the idea that if there's a difference, they're going to get these positive numbers and not have to deal with the negatives. So that's really all that they're doing, is avoiding negative numbers. So the notation here is that the mean of the first sample, we're calling x bar 1, and I'm calling again the after they've consumed alcohol to be the first sample. And then the mean of the second sample is x bar 2. And then we have this third column of differences. So this is calculated by taking each pair and subtracting them. So they took 102 minus 103 and got negative 1. 100 minus 99 and got 1. And they did this subtraction all the way down. And they ended up with this column of differences. Then they collected or calculated the mean of these differences. We call this D bar. I'm going to show you how to create this column of differences in your calculator really easily. I don't want you to actually do this separate subtraction. Your calculator will do it for you. But before that, I want to talk about the relationship between the mean of the differences and the sample means. So again, looking at the notation, D bar is going to be the mean of the differences, meaning they subtracted all the paired data and took the mean. S sub D is the standard deviation of those differences. And then we say mu sub D is the population mean for the differences. So looking back at our example, we had the first sample had a mean of 81.3, the second sample had a mean of 74.8, and the mean of the differences between all the paired data was 6.5. And I want you to see that if you subtract 81.3 minus 74.8, you get 6.5, which means we have a relationship here between the population mean for the differences and the difference between the population means. It's a tongue twister. So what we're saying is that D bar is equal to x bar 1 minus x bar 2. And if the relationship holds for the samples in that way, it's also going to hold for the relationships here, for the populations. So we're saying that the population mean of the differences is the same as the difference between the population means. In other words, it doesn't matter what order we subtract. We can either calculate the mean separately, subtract them and run the test on that, or we can subtract the paired data and run a test on the differences. Why would we do this? The reason we're going to do this is because we can then reduce a 2-sample problem to a 1-sample problem. So instead of looking at 2 samples and looking at their means, we're going to view the differences between the paired data as a single sample and then run a t-test and a t-interval on that single sample. All right, so let's look at this problem again, and I'm going to show you how to set it up in your calculator and solve it in your calculator. So we have the same scenario. Now it's going to ask, can you conclude that the mean reaction time for people with a blood alcohol level of 0.05 is slower than the reaction time for those who have not consumed alcohol? So we're going to start off by writing the hypotheses. And just like when we did a two-sample t-test, the null hypothesis is always that there's no difference. Well, how do we express that when we're looking at one sample of the paired differences? We would say that mu sub d is equal to 0, right? That once you do all of those subtractions, that this mean is 0. The alternative hypothesis, in this case, it's asking if the mean of those who have a blood alcohol level of 0.05, if that mean is higher than the mean for when they didn't consume the alcohol. So again, remember that they're subtracting in order. They're taking mu1 minus mu2 to look at mu sub d. So they're saying, is mu1 bigger than mu2? In other words, that the subtraction between the two will be greater than 0. And again, that's why they set up the table the way they did in the other order. So I want you to put this in your calculator. I want you to pause the video for a minute and put this first sample of data into L1 and the second sample into L2. Don't do the differences yet. I'm going to show you how to do that in your calculator really quickly. I don't want you to do the individual subtraction. So just put in L1 and L2, and when you're done with that, hit play again. Okay, so now that you have sample 1 into L1, so we put this into L1 and this into L2, we want to set it up so that L3 is L1 minus L2, and that will do the subtraction for us. So I want to show you how to do this. So when you're in the edit portion, I want you to see that I've got L1 and L2 here. What I'm going to do is move the cursor. See how it's right now, it's right below L3. It's where you would enter the data. But we don't want to enter data. We want to program L3 to subtract the data for us. So we're going to arrow up to L3, and I want you to see what it looks like. So I'm going to use the up arrow and arrow up to L3. And right here now, notice it just says L3. L3 equals. And we're going to type in L1 minus L2. L1 is down here, it's second 1, and L2 is second 2. So we're going to do L1 minus L2, and then hit enter. And notice that it fills in that column for you. So the calculator has done all the subtraction for you. So now what we want to do is conduct a t-test on L3, the sample of the differences. So we're going to do a t-test, and we're going to be sure to choose data. And we want to make sure that we're doing this t-test on L3. So we're going to go to Stat, Tests, go to t-test. We're going to pick data. Our mu sub 0 is the value from the null hypothesis, which is 0. The list, make sure that that says L3. And again, L3 is right here, second 3. The frequency will always stay as 1. And then we're going to put in the symbol for the alternative hypothesis, which is that mu is greater than mu sub naught. We'll calculate, and we get a test statistic of 2.6175, so above 2.5 standard deviations above the mean, which gives us a p-value of 0.0097. On the previous page, they told us that the alpha level was 0.01, and this is below that. So since our p-value is below this alpha level, we're going to reject the null hypothesis and conclude that we have evidence for the alternative hypothesis. We just want to make sure that we write the alternative hypothesis in the context of the problem. All right, so we have, since the p-value is below alpha equaling 0.01, so since it's below, we reject the null hypothesis and conclude that there is enough evidence to suggest that the mean reaction time for people with blood alcohol level of 0.05% is slower than the reaction time for those who have not consumed alcohol. You could say slower, you can say greater. It's either one of those is fine. Okay, so now that we have the results of our t-test, let's look at a t-interval. Since we know the reaction times are greater, how much greater? So we're going to construct a 98% confidence interval for mu sub d. And now that you have the data, now that you have your differences in L3, this goes really fast. We're going to do a t-interval, and the information should already be there. I'm going to make sure that we have data, but it's probably already chosen. So we'd set it up if we were just asked to do this separately with no t-test first, we would still set up L3 exactly the same way. So I'm showing you the data to show you that L3 is set up in exactly the same way we did for the t-test. And we'll go to then t-interval. And again, you want to make sure to choose data, and you want to make sure that your list now says L3, because it most likely says L1 if you haven't done the test before. Frequency is always 1, and our C level is 0.98. By the way, this also means that when you go to mix up your tests, really take a look, because you might then have a one sample t-test after this, so you have to change that back to an L1. Just be really careful of what it says there. All right, so we have 0.03732 to 12.963. So there's our confidence interval. When we interpret this, we say that we are 98% confident that the mean reaction time for people with a blood alcohol level of 0.05% is between 0.03732 and 12.963 seconds slower than the reaction time for those who have not consumed alcohol. So be sure that you're saying that the mean reaction time is different somehow. So we're saying it's slower. So the hypotheses, or the assumptions and conditions when you have paired data. So the first requirement is that you have the paired data. If you have two samples that don't have a natural pairing, and you have two independent samples, then you have to do the two sample t-test. The only time that you're allowed to do this pairing with the simple t-test is when your data is connected with each other. A kind of a trick to look for is, are the sample sizes exactly the same? If the sample sizes are different, you know you have a two sample t-test. If they're the same, you could still have a two sample t-test, but it could also be paired. So if the sample sizes are exactly the same, then you want to look at is there a relationship? Is it a before and after? Or is there some kind of relationship between the first one and the second one that connects the individuals within the samples and gives you that natural pairing? We still need our samples to be random. We need the sample size, since it's the same for paired data, we need the sample size to be less than 10% of the population size. And therefore, if we have those two things, we can then assume that the individuals within the sample are independent. Before, I was talking about the samples, but I still want to make sure that person 1 is independent of person 2. And then we need to make sure that we look at the nearly normal condition for the differences. So if we have a large sample size above 30, we don't have to check anything, but if it's lower than 30, then we want to look at those differences and see if we have any outliers or any major skew. So we're going to do one more example where I look at these assumptions and conditions. So we have veterinarians can use topically applied antifungal to treat certain foot infections in cows. Since these infections are often caused by living conditions, typically all of their hooves are impacted. To compare the effectiveness of two medications, researchers randomly selected 10 cows and applied treatment A to 2 hooves and treatment B to the other 2 hooves on each animal until the condition had cleared. The results report the number of days each of the 2 different medications were needed. Perform an appropriate hypothesis test to determine if there's a statistical difference in the effectiveness of the 2 treatments at the 0.01 level. So the first thing we're going to look at is the conditions and assumptions. And I'm not going to try to predict which one's bigger than the other one. I'm just going to put the first one into L1 and the second one into L2. So I kind of made sure that this table followed along with the paragraph. So I entered the data into L1 and L2. Remember that to get L3, I'm going to arrow up to L3, and I'm going to enter L1 minus L2. So I'm going to say L3 is equal to L1 minus L2. I always do L1 minus L2. I have seen people who switch those around. There's no need to switch those around. So L1 minus L2, and then we hit enter, and we have the differences. So I want to look at the box plot of the differences. So I went to plot 1. I want to make sure that it's on, and I want to choose the box plot here. And then I want to make sure that the X list says L3. Frequency should always be 1, and I don't really care what the marks look like. Once you have the plot on and you've chosen your box plot, we're going to go to zoom and then stat zoom. So zoom 9. So now we're going to click on zoom and scroll down to zoom stat and hit enter. So the box plot looks pretty symmetric, but I do have an outlier here. And that is a problem. I shouldn't have any outliers in order to run this t-test. I am going to keep going, but this is something that I should note if I'm writing up a report. I have an outlier here. It could very well mean that these results are not reliable and we should take a different sample. So we have a natural pairing between the 2 samples of data because we have the same cows and the same same cows in each one, right? 2 feet are in sample A and 2 feet are in sample B. The sample's random. I say both samples, but basically the cows are chosen randomly. And 10 cows is definitely less than 10% of all the cows. I grew up in Minnesota, went to school in Iowa. It's definitely less than 10%. So we can therefore assume that the individuals are independent. The problem lies in that when we look at the box plot of the differences, we can see that it's reasonably symmetric, but there is an outlier. But I am going to go forward and run the t-test on this. So here's our information. We put L3 as L1 minus L2, where this is L1 and this is L2. And we're going to then conduct a t-test. We need our hypotheses. The null hypothesis is always that there's no difference, so that mu sub d is equal to 0. This question asked us, is there a statistical difference in the number of days that this antifungal cream needed to be applied? So they're only asking us if there's a difference in the number of days for these two groups. Not is 1 greater than or less than. So we're just going to say not equal to 0. That would imply that there's a difference. And we're going to conduct a t-test with data. It's always going to be with data when we're doing paired tests. Mu sub 0 with a paired test is always 0. Sorry, it is not always 0. I do have an example where it's not, but it's almost always 0. In this case, it is. Our list is going to be L3. The frequency is going to be 1. And then we're going to say that mu is not equal to mu sub 0. So we put the data into L1 and L2. Oops, here, let me subtract. Let me go back for a second. I put the data into L1 and L2, and then I did L3 with L1 minus L2 and got that column of differences. So then I'm going to go to stat, tests, and do a t-test. Again, we want to make sure that we have chosen data, that the list says L3, and don't forget to double check your symbol matches your alternative hypothesis. And then we will calculate. And we get a test statistic of t equal to 1.5, which is not that unusual, which means that we have a p-value of 0.1679785. Just keep lots of values here. So that p-value is pretty high. It's definitely more than the 0.01 alpha level that it gave us on the previous page. So the previous page was 0.01. So our p-value is above this level, so we're going to fail to reject the null hypothesis. And we have that since the p-value is above the alpha level, we fail to reject the null and conclude that there is not enough evidence to suggest that there is a statistical difference in the effectiveness of the two treatments.